So I've opened up the
complex or something?
So let's get started. So welcome back after the break from all the snow. So we're talking about so assignment-based clustering today, and the most kind of famous version of this is the Kmeans clustering problem. So let's look at this. So let's look at the schedule first. So there's some disruption in the schedule because of the snow day on so last week on Wednesday. So the lecture I was planning to give on Wednesday is the one I'm going to give today. And then there's a clustering homework which was posted, and so it's due in so it's due so a week from so it's going to be due a week from Wednesday. After the lecture today, you should have enough material to do all that. So what is so and I think this was posted already. The first question was on the hierarchical agglomerative clustering. So I think that so I think this assignment should be fine. What I changed in the schedule is that there were 2 lectures on streaming, and I plan to compress these roughly into one lecture. I'll probably actually cut into some of the lecture on the clustering, so on the spectral clustering, to try and cover a little bit more in the streaming case. So what's not great is that I'd hoped to have this lecture the previous week on Wednesday, and then that's when this assignment would be posted. So this assignment will basically be so this assignment will basically be on the streaming topic. And so as it's now with this structure, I'd hope to have this kind of due here, and then we would hopefully grade it by the end of the week, and you'd get it back in time to use it to study for so the midterm exam here. But now you're only getting we'll try and post it still on this Wednesday, but you'd only be getting just a week after the lecture to work on it. So it's probably not the most, it's probably one of the least or not as intensive programming assignments. So maybe, so Mattia, do you agree with that? That this assignment on the frequent items wasn't too challenging last year? Or maybe it was tricky? So I don't know. So does this seem like an okay arrangement? The other option I could do is try to give that lecture on Wednesday in the original spot and move the spectral clustering lecture back a week. And then you'd have a little bit more time to work on it. I don't think I ask any questions now about spectral clustering on this homework assignment. So you should be okay even if that lecture is delayed. Any thoughts? So let's just do a show of hands. We'll either say swap these two lectures, or we'll keep it in the same structure it's posted. So just show of hands, who would like to just keep it the same way? It's more cohesive. And who would like if I swap the two lectures? So, okay, so so it's pretty overwhelming. We'll keep it the same way it is. If you really want to get a head start, there are like 3 people who want me to swap them, and like 80 who want to keep them the same. So that seems pretty reasonable. So if you want to get a head start on this, there are lectures posted from previous semesters you can find, and there are notes up there. So I don't think the homework should be too challenging. Okay, so the clustering assignment, which we posted last week Wednesday, I think in the previous version of this class, this was, I think, one of the assignments that I got more grief about a little bit, but I've trimmed it down this semester. So one of the questions which was more challenging, I made that as the bonus question. So hopefully that one's not too bad. Okay. So the other thing is that your data collection reports are going to be due on this Wednesday. Luckily, last week, Monday, we talked about what would go in the data collection report. Does anyone want me to review any of that or go over that again? Are there any lingering questions? Yeah.
Can you review what you said last week about problem 5? Well, what do you
Sure,
want
yeah.
to say when we're trying to simulate the data?
Yeah, so I gave you this list of things I'd like you to answer. And probably the most confusing one is I want you to think about, now that you've collected some sort of data, you start to think about its structure. I want you to give some thought to how would you try and simulate this data. And so what I'm asking is, can you think of an underlying model that this data might come from? And now, it doesn't have to be the full data and all of the kind of, like you might get some messy data, like if you're collecting web pages and you just want to analyze the text. I don't care if you look at the header information in the web page, just think about the text itself. And you may not think about actually the actual strings of text. You might think about the counts of the words inside the page. And maybe that's the model you're working with. So then you can simulate, okay, what would be a good distribution for the sort of words? Maybe I care about only the top 10,000 most common words. Probably that's too small, maybe 100,000, but let's say 10,000. And so then I'm going to get a count for each of these words on each web page. Should this be a uniform count on the word, or should it's skewed in some way, right? Like we'll discuss this later in the semester, but like if you look at distributions of documents, the words in documents in the English language, it's like the word "the" occurs like about 7% of all words. Okay, and then like "on" occurs like 3% of all words, right? So it's not a uniform distribution over all the words, right? So a uniform distribution over the word counts probably would make sense as kind of way to generate the data. You would get some weird effects, right? So just kind of put thoughts into it like this, right? I'm going from something abstract like a web page. I get down to some model that you want to be thinking in here, some abstract representation, say bag of words, could be kgrams, could be something else. And then how you generate data that looks like the ones you're collecting. So for instance, instead of just you're designing an algorithm, you want to see how it scales on much bigger data, how you generate data that might be kind of realistic. And I don't expect perfect answers, but I want you to kind of think about what this might be, right? So have some discussion about it, right? So if you've noticed on some of the homework assignments, I ask you these questions like, which algorithm do you think is better, right? And there's often not like a right answer or a wrong answer for this. I just want you to put some thought into why you think this one is better or worse, right? And it's kind of what I'm asking you to do here. This is an important thing to try and be thinking about when you're modeling, and so I'm just asking you to put some thought into that. So think about it, write down some words about it, and you should be okay. If it's kind of a mindless thing, I might be less happy, but the more thought you put into it, the better. And it's only one page, the whole thing, right? So I'm not asking for too much. So that help answer your question? Yeah. Okay. Great. Okay. So then we'll keep on this schedule. And then I'll post this as the frequent items assignment on Wednesday, and we'll give the spectral clustering lecture on Wednesday. We'll try and catch up. Maybe I'll introduce the basic column and streaming model on Wednesday, so you get a little bit exposure to it before you can when the assignment's posted. And then after that, we should be basically caught up to where we were. Okay. All right, so I want to talk about this assignment-based clustering, and we talked. So in the lecture last week, we talked about the input to a clustering problem is usually some data x and a distance d. Right, that tells you which measures how similar or how far away two points are inside the data set. Right, and so kind of you could think of having data, and we'll draw these pictures, which are going to be in where I'm going to have points, which is the data set, and these points might be in, they might not be balanced. We'll draw them in 2D as points just because this is easy, and this is again both a very fine representation of what's going on, and it's deceiving because usually you want to use this when you can't just plot the data in 2D. That's when this is actually useful. And then the point of assignment-based clustering is that we're going to, instead of the hierarchical where we define this procedure of how to build these clusterings from the bottom up, where we're slowly merging nearby points, the goal here is kind of a more precise, where we're going to set down an objective function, and then we'll talk about various ways to try and achieve this objective function. Where the hierarchical, it's not really clear what it was optimizing. It was kind of intuitively doing the right thing, but it was not so clear what the outcome was going to be, or how various decisions you make could possibly affect it. Okay, and so the case here is I'm going to lay down a set of these points called these so-called centers. Okay, so I'm going to have a center set, C1, C2, C3, and C4, and in general there's going to be k of these centers if we want k clusters. So usually you have k of these, and so these centers are going to implicitly define the clusters, right? So we had said that a clustering had the property that given x, I'm going to decompose it into these sets, S1, S2, up to Sk, so that Si and Sj were going to be disjoint. That they weren't going to overlap with anything, and that x was going to be the union of S1, S2, up to Sk. So it's going to be a decomposition of the space. And so I'm going to use these clusters to implicitly define this decomposition of the space. And so I'm going to define some function phi of c, which is defined on a point x, which is going to be the arg min element cluster one center in the set of these centers that minimizes the distance between x and c. Okay, so I'm going to find this function. So given the set of these centers, to find a function which, for any data point x in my set, is going to return the closest of the centers. Okay, so that's what it's doing. It returns the closest center. And I can actually, there's a nice geometry here when I draw this in 2D, where it's going to kind of decompose the space in a way that looks like this. And so basically anything in this whole region here is going to be mapped to C1. Right? And so if you remember from one of the lectures on nearest neighbor search, this is called the Voronoi diagram. And it's a way of decomposing the space of all possible objects or the domain that the data lies in, so that so given a set of centers, everything maps to its closest point, right? It's the nearest neighbor function. Everything in here maps to C4 as being its nearest neighbor. And so if I'm using Euclidean distance, then this Voronoi diagram has this really nice structure. I have these linear, these separators in between the points, okay? And they kind of form at these vertices. And in 2D at least, the complexity of this is linear in the number of cluster centers I have. Okay? In higher dimensions, this starts to break down, but this is underlying the structure that this function is capturing. So this is function, this nearest neighbor function is capturing this this Voronoi diagram. Okay, and it's implicitly saying all of these data points in this region are in this cluster C4. Right? So now I can say that this set here is S4, this set is S1, this is S2, and this set is S3. So I've implicitly defined these clusters based on which points are mapped to here. Right? So in general, Sj equals the set of points in X such that, this is my data set, that phi of C of X is equal to Cj. Okay, so I'm going to implicitly define the clusters based on this function and the choice of these centers, right? So now the clustering problem comes down to just choosing these centers, and then I just assign all the data points onto its closest center. Right, so this is the assignment-based clustering framework. Okay, and I can build this without kind of knowing a hierarchy of how, you know, these 2 points were linked before these 2 points. You know, in this case, I'm not gathering the information. I'm just mapping points onto a cluster center. Yeah.
And what about the edge cases? When you have points that lie exactly on the line of the diagram, do you consider them the outliers and you just discard them?
Yeah, so if a point is exactly on the line, you can either have some usually you'd have like a canonical way of assigning it. Say, always assign it to the lowest index cluster center, just so it's easy. There'll be variant to this. Maybe we'll talk briefly at the end of the lecture about you can do do soft clustering where you relax that each point is you relax this condition where this intersection may not be the empty set. You assign points to, you can say it's half in this cluster and half in this cluster if it's on the boundary. So there are ways to do that as well. Generally in this setup, this is by far the most common setup for clustering, you assign it just one way or the other arbitrarily. You know, ideally you would have enough data points that one point on the boundary isn't going to make that big of a difference. Okay, so now that we have this arrangement, and let me just write up this function again here so you remember it. Argmin. So the center in this clustering set between C and X, right? So it's the center which minimizes this cost. now I can go and define a few different, so I can find like a few different objective functions, and then say my algorithmic challenge is to try and find the centers which optimize these. And so the most common one, I'll call this cost 2 of a set X and C, is going to be, so I'm going to take a sum over all the data points, and I'm going to look at the distance between each point and its assigned center, and I'm going to take the sum and square. I'm going to take the sum of the squared distances. All right, so this is the distance for each data point X. I look at the distance to its center. Right? That's what's going on here. And I'm looking at all these distances and squaring them. And so finding C, which so find the set of the centers which is minimizing cost 2 is called the Kmeans, so clustering, so formulation. Okay, so this is probably the most famous version of clustering. So many people have heard of Kmeans before, right? So is this new for anyone? So maybe a few people, this is new. Okay, so this is kind of the most famous formulation. This is, sometimes people even, there's an algorithm, a few algorithms will describe, there's one that it's sometimes referred to as the Kmeans algorithm. Kmeans, as I will call it, is not an algorithm, it's a formulation, and we'll see multiple algorithms that attempt to find this solution. It turns out that this is kind of, as if you take an algorithms class, you say, how hard is this problem? What's the best runtime of any algorithm for this? It's, so it's actually very hard. So there are some cases where some weird data setup where this can basically take like very large so polynomial times that depend on D and K and N, the number of points, number of clusters, and the dimension of the data is. And that's for if you're looking at Euclidean distance. Okay, but we'll see some algorithms that work very well in practice. Okay. So this is the most common setup, but there are other options as well. There's cost infinity, which XC, which is equal to the max X. Right, so I did the same thing. Instead of summing over all of the squared distances, I've just taken the max of all these distances. So this is called the case. This is called the case center vary version of this. And we saw an algorithm actually last week, which I will review and say a few more things about, called the Gonzalez algorithm, which is a simple greedy algorithm that works pretty well in this case. Okay, so I'll describe it again in this context and say a few more things about how hard this is. But this finding the max distance, I want every point to be close to a center. I want no point to be too far away, right? Instead of the average squared distance, I want the furthest point. I just care about that. Okay, and then the last common version is like the cost 1. And this is, if you were to just write down what you thought the formulation should be without kind of knowing what the underlying algorithms are, you would probably describe this, which is just the sum of the distances. I'm not summing of squared distances, it's just the sum of the distances themselves. Right? And so this is known as the K, this is known as the K-median version of the problem. Okay, and basically this one is less well studied because it seems more natural. Like, why should I square the distances instead here? it turns out that there's an averaging trick you can use for the K-means variant, which is not going to apply here. Okay, you can do some other things to try and replace that step, and we'll describe this. I'll describe it in the context of the algorithms for K-means. But there's one step here that becomes much more complicated when you change the formulation this way. It seems more natural. I agree. It's actually more robust to outliers. A single data point far away from the center will pull the center away less because it's just the distance, not the squared distance of an outlier. So this is actually a more robust to outlier approach, but it turns out it's harder to kind of optimize for in practice. And then there's a version of this which is actually more common called the K-medioid, right? And so the Lloyd's algorithm we'll talk about and the K-means plus variant for K-means are built into MATLAB, as well as the K-medioid variant of this. Not the K-median, but the K-medioid. And the difference here is that this is, again, trying to look at this cost function. So this is trying to minimize cost 1xc, but such that c has to be a subset of x. This is a subset. So it only considers cluster centers, which are elements of the data set. Okay, so here the cluster centers could be anywhere. It could be any sort of object in the most general formulation, and that's the K-median. And that's also usually what people use for K-center and the K-means versions, although we'll see variants of these that have the centers as elements of the data sets, which includes the Gonzalez algorithm. But in the K-medioid case, there's a step here which is hard, so sometimes you replace it by just searching over the elements of the data set instead. So that typically is why you would use the K-medioid variant instead here. And so this ends up being much more general to describe an algorithm for this than here. I can use this for basically any distance function, where the versions are typically for the K-median and the K-means variant are usually for just the Euclidean distance. Those have special properties that we use to essentially search for the centers over all the data sets. Okay, so there are these variants here these are very commonly used versions of clustering formulations. And now I can write down a specific cost function, and I can say, I find a set of centers. How close am I to the optimal cost? Right? I can ask questions like this. Is this the optimal set of centers? I can now start to formalize this language a little bit, and you can give it to an algorithms person, then they can go and pound on it for a while. And this is actually what's happened over the last roughly decade, 15 years. Where these were proposed a while ago, and then about 15 years ago, people started saying, and in some cases longer, but kind of how fast can we solve these? How well can we solve them? How well can we approximate these formulations? This is much more formalized than the hierarchical, which is kind of more intuitive. Okay, so maybe we'll start by reviewing the Gonzalez algorithm for K-center. Okay, and so this will apply, and everything I will say about it will work for any data set X and D, which is going to be which is a distance which satisfies the properties of a metric. Okay, so as long as this is a metric on X, then this algorithm is basically going to work, and I'll be able to say something formal about how well this works. Right? Okay, so we went over this last week, but let's just review this algorithm. I think this is an under studied or in the importance of it in the algorithm. So we'll choose. So I'm going to incrementally, greedily choose these cluster centers, and I'll choose C1 from the data set X arbitrarily, if I can spell that. arbitrarily. Okay, so I'm going to choose the first center as any of the data points. Okay, and then one, I'm going to for j equals 2 to k. So I'm just going to greedily in a for loop basically pick the other centers, and now I'm going to set cj equal to the arg max of the elements in the data set. Based on the function, the distance to, write this way, the distance to cj minus 1 of x. Okay, where c of j minus 1 is going to be c1, c2, up to cj minus 1. Okay, so this is the whole algorithm here. I picked the first cluster, and now I'm going to have a set C1, which is just going to contain one center, right? And then I'm going to incrementally build a set of these centers as I go. And I'm always going to pick the data point which is furthest away from any of the existing centers. Each of them is going to get a score. It's going to be, and only one of the data points is going to be actually affecting this cost infinity score. That's the one that's furthest away from any of the cluster centers. And so the way to ensure that the cost goes down is I pick the one that's farthest away and I make that a center, and now the distance from that one to its center is 0. So that was the furthest, so now there's another one which is second furthest, and that's going to be a smaller cost, right? So let's just go through an example, and I can maybe say some of these things again in a similar way. Okay, so let's say I've got some data set here. I'm going to pick, is there a question? Okay, so pick one of the points as the first center, right? Now I look at the distance from every point to here, and I pick the furthest point away, which is going to be down here. All right, so now this will be C2, right? So now I have these two centers, and now implicitly there's this Born diagram which cuts through here, and these are kind of where the furthest points away are. Kind of have this bisector. And the furthest point away, essentially, like you had suggested before, is a point on the boundary, right? This is a point I don't have a good assignment to either of the centers. So then I will pick this guy as C3. What's going to happen now? Right, so now I can, right, so I didn't pick the furthest point away from C1, but the furthest point away from either. So now I'm going to get a new Born diagram here, which is going to look fairly degenerate, but sort of like this. These are going to meet off somewhere up here. Okay, so it always has some nice structure, but sometimes they're going to meet pretty far away. This is the new Born diagram. All the points in here map to C3. These map to C2. These look fairly good. These map to C1, but there's some kind of stragglers out here. And I picked the furthest point away, which in this case is maybe it's going to be one of maybe this point right here. Okay, so I'll pick this as C4. Okay, so this is going to add new elements to the Born diagram here. Something like this. Yeah. Probably these should meet, right? So this part is the same. Okay, and so now I've got this new Born diagram. Parts of them we have the same, represent the same bisector, should be the same, right? So I've only updated this in a local region, and then maybe I say if I said I wanted 4 clusters, I would stop, but maybe it looks like 5 would be good, so I'll pick another point down here as, say, as C, this will be C5, and now right, so now it assign all these into the 5th cluster. Right, so this seems like a pretty simple algorithm. to implement, and in this case it worked extremely well. Right? There were essentially 5 groups of points, and I placed one of the centers in each of those after 5 steps. All right, so any questions how this works? Yeah.
I'm actually confused how the Morgan diagram, like, I'm just having a hard time understanding what it's showing. Could you explain it?
Sure, yeah, right. So basically what I've done is, the Vornian diagram is here. I need to really conceptualize it, think I'm in 2 dimensions, right? And so I'm basically looking at this phi function, and I'm mapping every point to its closest center. Not just the data points, but any points in RD, right? And I'm dividing these lines, which are separated. The point on this line is the same distance from here as it is to here. That's what this is a bisecting line between these. A vertex right here is going to be equal distance to 3 different centers at the same time. Okay, and so by drawing these lines, I'm decomposing the space into regions which are implicitly defining my cluster assignment. Right? If I have this assignment of these clusters, the clusters here based on these centers, and I define this over the data set, but I could apply this over to the R2, the 2-dimensional plane as well, and say every point is assigned to some center, and that exactly corresponds with these regions. Yeah.
So I understand that C3 is the farthest distance from C1 and C2. Is C4 treated the same as the farthest from C1, C2, and C3?
Well, it's the furthest from the minimum, right? So it's the point which, so I wrote this a little different last week, but there's an arg max of these points, and this function implicitly contains a minimum, right? So C4, I don't map to the furthest of C1, C2, and C3, but I assign it to its closest point, which is C3, and that gives it a score. Right? So think of, after I'm at the point where I have C1, C2, and C3, I kind of draw lines from every one of the data points onto the center, and I do this, but it's going to get very, very messy. And I assign every point to its center, and then I look at the longest of these lines. Right? And the longest of these lines corresponds with the point that's furthest away from its center. Right? So it's a little it's a little confusing there. You'll implement it in your homework, and if you implement it correctly, then you'll understand how it works. But it's not too challenging, but just make sure that you get these representations right.
Apart from 2 initial points, all the other points lie on the line, basically, right? The line goes through them.
Well, it might not go through them. Like C4 is not exactly on this line.
It doesn't have to be.
It doesn't have to be exactly on the line. The line separates the Euclideans, the continuous of Euclidean space, and the actual data points are just points on here. So in general, they won't actually lie on the line. Yeah, they tend to be points that are close to the line. Right? So one way of thinking about how to implement this, and I wrote up some details in the notes, is to think about, I've got some data set X, and I'm going to store this as an array. Okay, so I'm going to have this array that goes from 1, 2, 3, 4, up to n. Right? So this ith point, this corresponds with xi. Right? I have the ith data point here. And in this array, I'm going to store this center assignment to an index. Right? So at the first round of the algorithm, when I just have C1, everything is assigned C1. Right? So everyone is given a value 1, because everyone is mapped to the closest center. And the first element, maybe that's what I picked as C1. So this one gets a distance 0. This one gets a, right? So this value here, I can store the distance from xi to c, I can store that in this column here. So maybe this is 0.3, 0.7, 0.8, 1.2, 0.3, and then I can compute this for all of them, and then I can just identify which one is the furthest distance. This one is the one I choose as the next center. after I do that, then I'm going to kind of update this array, okay, and so forth. And so this assignment, the first point is going to stay the same. Some of them are going to stay the same. Some of them are going to change to assignment 2. And the one that was the furthest distance, this one always changes its assignment to the new data point, right? So this one's going to have a distance 0, and this one had distance 0. And this one, if the assignment is the same, the distance is the same. It doesn't update the distance to the new center. But if the assignment differs, this was 0.8, right, then this one is going to shrink to 0.2. So most of these distances, if the assignment changes, that means that distance is decreasing. Okay, and then when I get a new center, I just need to compare the distance to the new center versus the cached distance I'd already computed. So if I maintain kind of an array of assignments, maybe even the distances, or I can recompute these on the fly if I want to, then I can kind of maintain the assignments implicitly based on the indexes stored in this array. And this is kind of a really kind of nice way to implement it.
So why did 0.8 turn to 0.2?
So that would be an example where this point was distance, say, 0.8 from C1, but now I chose center C2.
Right.
The distance is smaller to C2 because I changed its assignment.
Them, right? It's the difference between this new center and this point.
It's the distance. The distance.
Right. So if it was 0.8 and the new center is 1.2, shouldn't it be 0.4?
This was the distance to the it probably has to be larger than this because of triangle inequality. Yeah, so maybe this is 0.6 or something. It doesn't have to be exactly 0.4. That would be if it was on the direct line in between. So if it's off to the side, it has to be larger. Yeah. Yeah, so it may not be exactly 0.4, but you're right, it should be at least 0.4. Right, so this, let's make it 0.6. Okay. Okay, so this is kind of a super simple approach that works pretty well. Okay, so why is this not always used, right? Why do people use these other algorithms? What's going wrong with this, right? Well, what could be an issue with this, running this algorithm here?
Did you make an outlier center?
Sure, yeah, right. So if I have one data point which is an outlier, I'm always going to pick that as a center, right? And so it's always going to pick an outlier point as a center. And so that's not really capturing the shape of the data. It's capturing kind of, I'm finding all the outliers, right? And so this does poorly with outliers. I mentioned that the K-means or the K-median version was better with outliers than the K-means. Well, this is even worse, right? So this does poorly with outliers. And it tends to pick the centers, even if these centers are, there aren't really any major outliers, it's kind of picking them on the boundary of the data set here, not really in the center of each of these groupings. Turns out I grouped them just fine in this case, but in other cases there might be some boundary points, and I would tend to get those wrong if I'm picking these on the extreme. Right? So it's not quite optimal. Again, I said this was supposed to optimize this k-center version, this cost, this infinity cost, right? The max infinity cost. How well does this algorithm do? Is this going to give me the optimal solution? No, it's not going to do that. That would again be better if I move these points somehow into the center of these regions, right? If I, instead of picking this extreme, I pick some place more central, this would do a better job. So it's not doing perfect, but what I can say about this is this provides a 2 approximation. Okay, so what this says is that the output, let's call this output C hat, and let's call the C star equals is the optimal set of centers. And this means that it's going to be the true argmin of this cost infinity of xc. right? So the true argmin is going to be C star. And so then the 2 approximation means that the cost infinity of x c hat is going to be less than 2 times the cost infinity of x c star. Right, so if this is the optimal possible cost it could be for any set of centers of size k, then I'm going to guarantee it's going to be no more than twice that big. It's going to be less than 2 times the optimal cost. Okay, and it's not, it's, so it's not, you know, it's not too hard to see it. I'm not going to go through the actual proof in here. But you know, it turns out this holds for any distance which is a metric. If the distance is a metric that I'm using over the set of objects, then this algorithm will always give a 2 approximation. And it turns out in general for metrics, you cannot, it's NP hard to do better than a 2 approximation if all I know is that the distance is a metric. If I have a data set in 2 dimensions, I can do a little bit better. There's like a 1.7 approximation algorithm that you can do that runs in polynomial time. That's not NP hard, which means that we basically expect it's going to run in exponential time. But to do something like, it's known that, for instance, to get a 1.5 approximation, even for data in Euclidean 2 dimensions, it's NP hard to get a 1.5 approximation. There are some data examples where you can't do better. And so in practice, this works better than a 2 approximation. Okay? So it's a very simple algorithm, and it's basically as good as you can do in theory. Yeah.
Is there any type of like variant that tries to control for the outlier problem on this?
Yeah, so if you care more about the outliers, you would probably, I mean, this is specific for the k-infinity cost, and the k-infinity cost is actually, it's better if you choose outliers as center. That will give you a lower cost, right? So if I want to control for the outliers, I probably want to use the k-median cost function instead, right? So then you want algorithms for that. And we'll see for the, we'll look, I'll describe the algorithms for the k-means formulation, and that one is better with respect to outliers than this, and that will actually be a good thing you can do after you run this algorithm as well. But this is kind of like a really nice and easy starting point for any sort of clustering. Works for any distance metric. I can basically use this way of storing these distances in these array, and if I don't have to recompute all the distances, so it runs an O of n times k time. I make k passes over these arrays. Find the maximum, and then I update all the distances, right? And that takes linear time each pass. I make k passes, right? So it's a pretty simple algorithm to run, and it's roughly linear time if k is a constant. Okay, so let's move on to the k-means formulation. Okay, and let's talk about the most common algorithm, which is called Lloyd's algorithm. Okay, and I imagine a number of you have heard of Lloyd's algorithms. So we'll start by I'll review this kind of quickly, and we'll talk about it and how to kind of improve upon its basic form. Right. So this was invented by I forget Lloyd's first name. Lloyd was his last name. I think it was at Bell Labs in like 1957, and he just wrote a internal tech report, and he didn't publish it till 1982 when people realized that this was actually pretty useful. So after a lot of nudging from his colleagues, he finally published it. Apparently he'd been doing some experiments with it, and partway through the experiments, this was in 1957, they upgraded the machine he was using, and he would have had to rewrite his code to use on the new machine. They weren't as naturally compatible anymore. So he's like, I didn't finish experiments, and he just kind of put it aside. So the published paper in '82 kind of is the original tech report, but describes saying why he stopped at this point. So now this is used everywhere. Okay, and he originally looked at this just for points in one dimension, actually, as a way of compressing data across a channel. Okay, so Lloyd's algorithm. So step 0 is I'm now going to start by choosing, I'm going to choose k points C, and let's say they're going to be a subset of the data set. Doesn't necessarily need to be, but so I need to somehow choose the first k points as the choice of these centers. So I'm going to start with the set of these centers, and now I'm going to repeat. This is going to be an iterative algorithm. It's going to have 2 internal steps. So for all of the data points, I'm going to assign them to phi of c of x. So I'm going to assign every data point onto its closest center, right? So I'm going to actually compute this distance to from each point x to each of the centers and assign it to its closest one. And so this will be representation. If you remember, Sj will be all x in these data points that we just defined it implicitly before, so that phi of c of x equals c of j. Right? So I said implicitly it defines these clusterings before. I'm just going to explicitly compute them inside of this algorithm in step 1a. And then 1b is that I'm going to then adjust the centers. Okay, so now for all j in 1 through k, right? So for each of the clusters, I'm going to readjust the center to be the average of over Sj. So I'm going to look at all the points that are in this cluster, this guess of the cluster, and I'm going to reassign the center as the average of these points. Okay, so in order for this, and then I'll just kind of, so I'll repeat until C is fixed. So C is unchanged, right? So this is the algorithm. So now this iterative algorithm, where in one step, I'm going to assign points to the closest center. This was implicit before. And then I'm going to recalculate the center as the average of all the data points in the cluster. Right? So in order for this averaging step to actually be well defined, I'm going to need that the distance d is going to be equal to the Euclidean distance. So this is going to be the standard straight line distance between vectors, which is kind of the most obvious thing to use, but I'm going to need to explicitly say that it's the Euclidean distance at this point. There are other things you can use, and this will still work. Like I think the cosine distance will still be fine effectively, but usually this is specific for the Euclidean distance. Okay, and that's because this average step is actually going to do something meaningful with the Euclidean distance. That this is going to be the choice of assigning the center, which is going to best kind of fix the clusterings. Okay, so let's kind of run through kind of a simple example of how this might work. Okay, so I could start with maybe an initialization where I've got 3 centers and they're all here. Okay, so this is actually not a very good choice of the centers. These are going to imply some Voronoi diagram here where all of these points are assigned to this one center. Right, so this isn't very good. But what's going to happen is that in the first step, so like this implicitly, all the these are the first 3 things, and implicitly, for the 1a, I will assign all the data points onto here, and this will be kind of, if this is C1, then everything in this Voronoi cell will be S1. But what's going to happen in the averaging step is it's going to force it out to C1 is going to be forced out to here. Kind of mainly the average between these two groups, and being pulled a little bit by these points here, which are still assigned to it. And these two clusters might move a small amount here. Maybe this becomes C3. Okay? And so then this is going to give a new Voronoi diagram here. Okay, which is a little bit better. This C1 now does not include these points, and these might shift a little bit here. So now I'm going to get C2. Maybe this one, maybe this becomes C3, and now C1 is out here. And so it's probably going to get stuck here just a little bit. If it had been shifted, let's say, if I'm lucky, maybe I'm going to have one data point here also. So now C2 got pulled a little bit in this direction. And then I can run. So if I didn't have this data point, it might stuck and it might get stopped here. This is probably not the optimal thing. I have two centers assigned here, one in between these two groupings of points. But if I have this other data point here, it's going to pull C2 in this direction. Right? So now C2 might move here. C3 might move up a little bit here, and C1 might end up getting pulled a little bit away from this point because it's no longer in there. And so now C1 is here. And then if I update this Voronoi diagram, it might look like this. And then in the next step, C2 will move up here, C1 will move a little bit further down, and they'll keep rotating until I get C3 here, C2 here, and C1 down here. And they'll keep adjusting to the centers. Kind of makes, okay, so who's, a few of you haven't seen this before, probably, but hopefully this kind of basically makes sense how it works. If I were to start with this assignment here, what would happen is that I would run it once, and each of the centers would kind of move to the average here. Right? And it would kind of adjust them to right where the group of points is supposed to represent be. Okay, so what's nice about this is that you can show that this algorithm will always be, every step is going to be decreasing this cost2 function, right? So you guys say that every time I do either 1a or 1b, this cost function is going to be, is decreasing. Every time I assign a point to the closest center, well, if I remember cost2 of x and c, this was from, I can write this as the distance from x to, you know, its corresponding center. Right, and so if I assign it to a closer center to actually its minimum, then that data point, this has to decrease. Okay, and I can also write this as sum over j, sum over x in Sj, d of x Cj, right? So I can run sum over for each cluster center. So for each cluster, I map all the data points at Sj onto Cj, right? And so I've just broken this sum down into a double sum. Each point is counted once. And so if I look at just the cost for one center, when I'm reassigning the center to the average, it turns out this, for Euclidean distance, this must also decrease. It turns out the point that minimizes the sum of the squared distances is the average. And you can write down a kind of this cost function, and you can take the first derivative and show that the first derivative is 0 when you set the point to be its average. Okay, so by taking the average, it's minimizing this step. So that's also decreasing the cost. So that means I'm never getting into like an infinite loop, which you think for iterative algorithms, you might be a little bit concerned about this. And there are other versions of the iterative algorithms. If I use a different distance function, I might get into an iterative loop where keep assigning points back and forth between two cluster centers and it never ends. This can't happen here. The cost function will always decrease. So that means I can never get the same assignment twice. And so in some sense, it's converging. The number of steps that might converge might be an exponential many steps, but generally these weird adversarial kind of data sets. In general, this works very well. Okay, yeah.
So in our example, you were saying like, well, if we're lucky, we have this data point that'll pull the centers away. So what do you do, like, if you don't get lucky? Do you just run this multiple times and you expect like with the randomness that it will kind of give you the right thing?
Yeah, right. So that's exactly the right thing to do. You actually should run this multiple times. And you want to kind of seed this in a way so it's not the same set of centers. If I choose the first 3 centers the same every time, it's deterministic after that point. So that's not going to help. So I somehow need to introduce some randomness into here. Right. Yeah, so but that's exactly what you should do. And I'll kind of say something more specific just in a couple minutes. Right? Right. So the first thing I want to mention, the number of times you should go through this repeat. This may slowly decrease. It's going to decrease a lot at the beginning, and then sometimes towards the end, it really slowly adjusts towards the optimal solution. It might eventually stop, and often for really nice data sets, it will actually stop pretty quickly if it find the right solution. But it might run thousands of steps. It could be worse. So often you cut it off after some point. Run for 20 iterations. That might be fine. If k is larger, you might want that run for even more iterations. Okay, or you can just look at the cost function, and when the change between the cost function of 2 steps is sufficiently small, then you can also stop. That's another thing to do. You're basically, every time you do a reassignment, you're calculating what the distance is, so it's easy to kind of figure out what the cost function is on the fly. Okay, so I'd say generally 20 steps should be more than enough in a lot of cases. Okay, so the question is, and I need to do these random restarts where I restart over again randomly. The question is, how should I do this first step here? How should I choose the first set of k centers? What would good ideas be? So randomly. Yeah. So arbitrarily, it's not random. So that might not work well. If I just pick them uniformly at random, this might work okay. But if I have some imbalance, like 90% of the points are really well concentrated here and not as many in these other groupings I want to hit, then this may not work well. I may almost always pick points here, and that might almost always get stuck. So actually just purely at random doesn't actually do that well. In some cases it's fine, right? But there are some cases which are not too unreasonable where it might almost always get stuck in the same sort of situation.
So hint is like Monte Carlo distribution where it's like really uniformly distributed across the space.
Yeah, so I wanted to somehow balance random sampling, uniform sampling over the points, but also to be spread across the space. Yeah. Yeah, so another good idea is to use the Gonzalez algorithm. Right? This is also a really good way to see this. And unfortunately, it's not random. So if I end up, the Gonzalez is deterministic the same way Lloyd's algorithm is, right? So if it ends up getting me in a bad situation, it'll always do that. And uniform at random may not work either. So it turns out you want to do something kind of in between these two. Okay, in between randomized and Gonzalez. And that kind of, if you add these two together, you get something called Kmeans plus plus. Okay, and so this is what I'll describe next. This was a very clever naming. There were two papers that came out about the same time, and one set of authors called their algorithm Kmeans plus plus, and everyone cites their paper now. So it's cool. It's important to have a clever name. So Kmeans plus plus. Sometimes this is called d squared sampling. Okay, is the idea, and this is a way to initialize Lloyd's algorithm. And so the idea is that you would rerun this some number of times. I think that they write some guarantee that if you run it like 8 times, then you're with good probability, you're expected to find an approximate solution, something like that. So in practice, run it a few times, and if they're consistently getting the same answer, you're probably that's probably good. Okay, so this is so again, it's going to be a simple algorithm that's almost as simple as Gonzalez algorithm, but it's going to be a little bit more complicated. So again, I'm going to choose C1 in X arbitrarily, and this could be at random, but you know, all the analysis just assumes it's just any point. And so we'll say, like Gonzalez algorithm, this will be a single cluster. I'll have one cluster center, C1, which is the first point I picked. Okay, and then I'm going to say for j equals 2 to k. I'm just going to kind of greedily build up these cluster centers the same way as Gonzalez algorithm. But now the key step is I'm going to add some randomness in here. And so I'm going to choose ci from the set X, but I'm going to choose it with probability the probability is going to be proportional to the distance from X to the distance from X to its assigned cluster of the one so far squared. Okay, so the same way with Gonzalez, I kept assigning these centers, and I kept kind of keeping track of the distance from every point to its closest center. And now I need to sample them randomly, but if that distance is larger, I'm more likely to choose that point. Okay, so this is the whole algorithm. So let's say I've got some data points here. Okay, and so I pick the first point, C1, and everything I compute the distance to C1, and so the points further away I'm more likely to pick, proportional to the squared distance. Okay, so there may be fewer points in this cluster, but they're further away. And there's more points here. So let's say I pick C2, maybe it's going to be C2 is this point. And now I'm going to assign every point to its closest center. And these points are equally far away roughly from C2. So I'm probably I could pick another point from this cluster center, but the distance is small. So I'm probably not going to, unless there are a lot of points. Right? And now with these points here, I'm going to pick probably from one of these two cluster centers, and not necessarily the furthest point away. Their distance is roughly the same, so the probability is roughly the same if I pick any one of these points. And then all of these points have a small distance to one of its cluster centers. These points have a large distance, so I'm more likely to pick here. But I might pick another point from one of these cluster centers, from one of these clusters, right? So and this is kind of how the algorithm runs. Instead of deterministically picking the furthest point away, I pick it away with some probability proportional to the squared distance to its assigned center. Okay, and so this kind of balances these this spatial approach where I try and want to cover the space, and also kind of some uniformity on the data point. So roughly any of these data points were roughly equally likely to be picked because they're all roughly as far away. And so you can show even for like as adversarial as you want to make the data, if you randomly do random restarts in this way, that you'll say that you'll with some probability you'll have a approximately correct solution after if you seed Lloyd's algorithm in this way. So this is now kind of a default. A lot of libraries. This algorithm is only it was from when I was in grad school. So this is from, I guess, 2007, and now this is built into about 10 years ago, and this is now built into most libraries that run for Kmeans. They'll do random restarts with this, and then they'll run Lloyd's algorithm, and this is the typical. Yeah.
Are there constraints on the distance here too? Or?
I can run this with any metric. Yeah, I don't need the averaging step here. Lloyd's algorithm would, but this by itself, I think, gives a worse approximation than running Lloyd's. But this doesn't have any kind of constraints about it being specifically Euclidean distance. I could use like Jacquard distance here, and it would give me something that is trying to optimize this K-means objective with Jacquard distance. If I want to do the K-median objective, I should do proportional to just the distance, not the squared distance. I can plug that in instead. Okay, so I'm going to ask you to implement this in the homework, and there might be one step that you're like maybe puzzling, like how do I actually do that, right? I need to pick something, not a uniform distribution, but proportional to some distance squared, right? Some bound, right? And that might not be completely obvious how to do. So it turns out there's a very simple way of how to do it. There are kind of more efficient data structures that can be done but there are more efficient data structures if you're going to draw repeated samples. But if you just need to draw one sample and recompute all these probabilities, there's a technique called the partition of unity. So okay, this idea called partition of unity. And so what I'm going to do is I'm going to have this domain between 0 and 1, and basically I'm going to set, I'm going to pick a uniform value between 0 and 1. So U, and that's going to index somewhere in here. So this is, say, U equals 0.432. Right, will be some point in here, and I'm going to use this somehow as my only randomness to select something. So how do I do that? For each of the data points, I assign it a weight, which is going to be its distance squared divided by the sum of all these distances. Squared, right? So I look at all the distances, I assign it, and I look at its distance squared, and this is basically going to be a probability distribution. So this is how I get weights, and these are proportional to this distance squared. I'm just kind of normalizing them, right? So I'm basically I'm doing an L1 normalization of the vector, right? So I compute a vector of all the squared distances, and I add up all these squared elements. But I store the square elements, so it's an L1 normalization. This becomes a probability distribution. Okay, so each point xi, right? Each point xi, or make these j's. So each point xi is going to get a probability that it's going to be chosen. This part is straightforward. I can get the probability. So now it's with probability this weight, and that's going to be proportional to the squared distance. And then how do I map it into the structure? Basically, I'm going to say that I'm going to kind of map this as weight of x1. If that weight is, say, 0.08, then it's going to get a length here, say 0.08. Right? That's going to be the length of this unit. Then I'm going to stack next to it weight of x2, right? And its length is going to be say 0.07, so that the sum of these is going to be 0.15, right? So I can kind of build this cumulative map of all the points, and it doesn't matter what the order is. And I'm going to partition this unity by these weights, right? And then when I pick a uniform random number, it indexes somewhere into here, right? So maybe weight of x3 is bigger. This was weight 0.21, so this is a bigger chunk, and this indexed into this cell associated with weight of x3. And this allows me to choose a proportional, and this chooses, so if this was the u I picked, the uniform random value, then it would map to point x3, and that's the one I select. Okay, and I can either store them in this way, or I can just store the cumulative weights. So I can think of writing wj is equal to the sum equals I equals 1 to j of w xi. Right? And then if I have these uppercase weights, I need to find the smallest j, where uppercase wj is greater than u. The smallest j where it's greater than u, that would correspond here, and that means u fell in this bucket. Right? So this would be uppercase w3, would be the cumulative weight up to here. Okay, so again, it's pretty simple to implement. If you look in the the math for data book in section section 2.4, M4 data section 2.4, there's an example that goes through this partition of unity idea. Is there a question?
So the value of the weight determines both the width of that bin and the value that is given?
Well, so the value of the weight gives me the width of the bin, and I have a cumulative weight of everything up to this point, right? And then u is chosen uniform at randomly, and it indexes into the structure I built. So I first build the structure, then I choose the point, a uniform value between 0 and 1, which is common built-in operation, and that allows me to index into here. And I can do that by linear scanning. I have to build this array each time, so I might as well do a linear scanning. But you could do a binary search, for instance, if these weights are static. But they change every time, so I have to rebuild it. Yeah, if you have too many points, so what's going to happen? That's when I just have points chosen, this one, C1, I can kind of think of this whole region, and I say there's kind of a very small region associated with all the points nearby. I might pick another point nearby, but then there are going to be these big chunks into cluster 2, cluster 3, and cluster 4, and they're going to kind of act in, it doesn't matter so much which of those points I pick, as long as I pick one of those points, then I get a point in that cluster. Right, so kind of think of it, I'm kind of decomposing this probability into these regions, and it depends on how far away the cluster is and how many data points there are there.
There's no order for this table.
Yeah, there's no order. You could think of ordering them consistent with the actual clusters, which you don't know, but it doesn't really matter. They're scattered all around, but I can think of them as a unit. Yeah, I could, if I knew what the real clusters were, I could reorder them, but it won't change how the probability is mapped. Okay. All right, so I just want to say one more thing here. I was going to mention this mixture of Gaussian's technique that allows you to do a soft clustering where you assign a point to a cluster center with some proportional to its weight. But I want to just quickly spend just a couple minutes on choosing the value k. right? All these formulations are given a distance, a data set, and actually now a value k. I say I want k clusters. How do I choose k? Right? So there's no really good answer to this, but one useful way is called the elbow technique. Okay, and this is just kind of an intuitive way how to do it. And what I want to do is plot as a function of k what the, say in this case, what the cost, what ck is, right? So say I have the cost I'm using to evaluate when I have k clusters. And as I change k, what's going to happen in this plot is typically it's going to kind of look as if I have only one cluster, the cost has to be larger, right? So it's going to start high, and as I eventually, if k is equal to n, the cost will be 0, right? So I also know I'm going to be down here, and typically what's going to happen is it's going to kind of come down and then plateau, and then kind of go out to 0, and there's some region down here which is like the elbow, right? Right, so you've got some hand at the end here, right? And so you can run this with different values of k, and then kind of guess where the elbow is, and this kind of tells you what value of k to use. Right, so then this is probably a good value of k, is going to keep going down no matter how large k is. So there's not one right answer, but at some point I'm not going to be gaining a lot on the cost function. So what's happening is I'm going to be splitting a single cluster into two sets, and so the overall distance, the cost is not going to go down that much. Whereas I'm going here, I'm taking two faraway clusters and I'm splitting them, and that's actually doing more gain. But after here, it's kind of plateauing. And so if you don't know anything about k ahead of time, you run it with multiple values of k, and then you kind of see what's happening, right? And the Gonzalez and the Kmeans ++ algorithms do this naturally, right? You can see the cost function decreasing, and so you can just run it past where you really need to go and then backtrack at some value which is a reasonable elbow. Or you can fit Lloyd's algorithm into the mix if you want to as well. So this is about as good as you can do for some choice with value k.